Okay, last lecture, and not last, but not least. Most. I'd like to review the stuff we did a little bit, which is on that slide over there from last time, and then we're going to go through it again from a different point of view, and we'll also look at some animations of actual space-time things happening. Lighthouses making light waves, ships going by and counting the light waves, so that you can see simultaneously with that animation something going on the space-time graph that we'll review a little bit first. But then I want to go ahead and get us into the other way to look at all of this that involves a transverse parameter, stellar aberration angle, which is a wonderful complement to our rapidity. And it's an invention of Lewis Carroll Epstein, Professor Emeritus at City College of San Francisco. And we'll advertise his book in the process. The idea of connecting those two is really beautiful, so we'll be doing that. And then we've started this all with Occam's razor, so we're going to introduce a little geometrical sort of tool that lets you do pattern recognition, and I call it Occam's sword, and you'll see why when we look at that. And I'll use the sword on some waves in a waveguide, some complicated spherical waves, and they're much different from the plane waves that we've been looking at, and also accelerator radiation, different colors at different angles. And then we're going to read something really elementary, go back and review all of this, and really learn about sin. Well, sine, that's the abbreviation that I'm used to, and cosine, and all of the trigonometric functions that allow us to do the relativity in this wavity. Then we'll just go ahead and just in really one page derive relativistic quantum mechanics and see what mass is, really get a feeling for what that is, the elephant in the room I call it. And then see all of the stuff that we did with action, Lagrangian, Hamiltonians, and things like that, Poincaré's identities, they all come out of the geometry that's contained in what we've really already done, but we can look at it many different ways. We can also do transitions if we get a chance. The time is going to probably be running out about in this neighborhood. I'll show you that the rocket velocity formula is essentially exact result for Compton recoil. Compton formulas are usually very complicated. This makes it very simple. And of course, the second quantization and all that goes with this is really out in front, but some of it is hidden.
Is there a geometry for that?
Yes, definitely. We have geometry for the Feynman diagrams. And you already have done it, you just don't realize it. Mm-hmm. Acceleration is also interesting. Of course, transitions involve acceleration, but this is another way to look at it. So let's get going here. The first thing is to review this little thing we did. And the idea was that we went through and looked at what a standing wave would look like to somebody that was moving, in this case, 3/5 the speed of light. And so when that happened, the nice Cartesian 90-degree coordinate system made by the zeros of the group wave, those were the things that stood still. And in space of a micron, and in the time of a femtosecond, traced lines that were vertical and perpendicular to the lines that the phase, a part of the wave, made when it became zero. and those were, of course, horizontal, and because they only appeared for an instant, that's what you call an instanton in some fields of physics. Because of that, they were going infinitely fast. That is, they were crossing the screen in both directions infinitely fast. They're just there for an instant and they were gone. And that made Cartesian graph paper, which now has been warped because the Doppler shift has occurred. Red on one side, in this case we have a Bob looking at a laser that's coming at him at the speed of 3/5 of light, and he's running away from a laser of the same frequency, but he doesn't see the same frequency. He sees infrared 300 terahertz for that, and the result is this very warped Minkowski graph paper made out of zeros of the laser waves. And we cataloged all of the dimensions, and I want to go over those in a little bit of our review here. We actually have a more compact way to describe them, but the functions that we're plotting here, or that are being measured here, consist of the hyperbolic trigonometric functions, particularly sinh and cosh. Those are the coordinates of these two vectors. In this case, the cosh is the vertical coordinate, and the sinh is the horizontal coordinate indicated by the blue dashed line there. And this one is a solid arrow going up there. And then you just flip the coordinates, put the cosh down here to make the horizontal coordinate of the phase vector, and then the sinh is here. And the numerical values for this particular case here, where the speed, that is the group velocity, is 3/5, 0.6, the values for the hyperbolic cosine is 1 1/4, and you can see that's right here, 1.1, 1.2, 1.25, and then the other coordinate, the sinh, right here, that's this is 0.75 on this scale, so it's coming right down there at 0.5, 0.6, 0.75. Okay. Now there is a problem with this particular speed. We picked this speed because it makes a 3, 4, 5 triangle, so all of the relativistic functions are rational fractions. The problem with this particular one is that these two values here, 3/4, 0.75, and 4/5, 0.8, are pretty close. And with all these fat arrows and thick lines, there is not too much difference between 0.75 right there, and let's see, what is this? Let's see, what have I got here? I've got 1.25 here, and then 1.333, that's this one right here.
Get a pair there that are real close.
Those two numbers are pretty close, and so are these. Okay, and that makes it a little hard to see what's going on. So we're going to look at another speed, 4/5, as we go through a review of the geometry of this coordinate system. Now the one that's being pointed out here, I would say first, perhaps this one is first, that's the most famous, but this is the next most famous, and that is the length contraction here by 20%. The length contraction that I'm talking about is a contraction from what used to be 1 unit and has now dropped down 0.2 or 20% to 0.8, the 4/5. That's this one. That's the hyperbolic secant that in our geometry, in our notation, that it's called the Lorentz contraction. Now it has an old-fashioned formula. This is the old-fashioned notation here, where you're using as your parameter what's normally labeled beta, and you'll see this in every textbook about relativity, practically. And that's the ratio of the velocity of the observer, but that velocity is the group velocity. So V group over C is U over C. The U is V group, and then the ratio of them is beta, and that is 0.6 here, 3/5. But the length contraction that we're talking about is the square root of 1 minus beta squared in the old notation. That's a secant. Now, that contraction can be seen as the track, the distance between the track of the group velocity. Something with a group velocity that used to be a coordinate with 1 unit for its separation. These two, this would be the axis, and then there was another one that was 1 unit that would have gone right through there. That's Alice's coordinate as she sees it, but now she's coming at Bob with her laser, and Carla's on the other side with her laser, making this coordinate system, which has shrunk, you see, the distance between those originally vertical lines. They're now not vertical anymore because they're moving at 3/5 the speed of light. And that shrinking right there is indicated by those arrows, and that is that number right there, 4/5. The time dilation is looked at differently. It's not a distance between lines, it's simply the height of this vector right here. That is the next tick after the one that was at origin is there, and it takes that much longer than that. That's where it should have ticked, but it didn't tick till there. That's the time dilation. It took 25%, that's more than 20%, 25% longer. That is, it took 1.25 units of time to happen. So all of the stuff that you're familiar with from the standard, I say, terrible presentation of relativity is contained in this one. But there are a lot more parameters in there than 2, you say. And in fact, you could say that length actually dilates and measure this distance over here, and you get 1.25 for that instead of 0.8. And you could say that time actually contracted if you measure where these things, where this line crosses right there, okay, it's contracted to 0.8. And those are all taken care of automatically by the pieces of the wave that we're working with here. Namely, its wavelength. This was the group wavelengths, and it is showing a contraction, okay? And this thing right here is the frequency new phase, but we can't really look at frequency until we count distances between those zeros, which we will do shortly again. But nevertheless, that's a lengthening. But as you can see, the waves kind of map it all out in space and time pretty nicely. And the most mysterious, perhaps, of all of the effects are the first order ones. The first order one, of course, being that I see a velocity. This tipping right here is linear to start with in velocity. Okay, that is the hyperbolic sign. Okay, which for small rho is just rho. So it's linear in the rapidity, linear in beta, linear in U over C. The other thing that is linear is the tipping of this axis. That is the thing that makes it so Bob sees into the future over here of Alice and into the past over here of Alice. You see, Alice would say everything above that line was future, everything below that line was past. Not so, according to this observer who has this coordinate system, namely Bob. He sees that as the future, that is the past, at time equals 0, and of course marches along with time. So those are about as much as I have to say in a review of this particular figure here, except to point out that this graph here made by the zeros is due to Herman Minkowski. And you can see that he's about 5 years younger than his student. So he was something of an academic star, whereas this is the lazy dog. Okay, according to him, right? And then the sad part of it is that 1905 is when he has his miracle year. Minkowski immediately sees, because he's been working on it too, with his graphs, that that's the way to understand it, and he writes to him, and usually he replies. Didn't reply to Minkowski. So he didn't get a chance to do it again. He died in 1909. Okay, so this is a little sad story. Relativity would be way ahead now if a lot more people had had that graph. Not just the waves, just the, you know, working the equations into a graph. That's what Herman did. Okay? Well, anyway, let's go ahead here. One of the things that I want to point out is that we deal with areas in space and time. They're of interest. Over in the momentum and energy things, it's action, but here it's interesting to see how the baseball diamond made out of the left laser and the right laser, which originally was here, but then if you move those pair of lasers toward an observer, in this case running away from the left moving wave, which means there was a laser to the right that's owned by Carla, and moving toward, that is moving toward the laser beam on the right, and of course that's off to the left, being owned by Alice, okay, and Bob sees that one elongated. Well, in order for the geometry of the waves to work, this one has to be shortened by the same proportion. If this one is made 3 times as long, this one has to be brought down to a third. In this case, this one is made twice as long as it used to be. It used to be right here at first base. And therefore, this one has to be made half as long, and there it is halfway to first base on this chart. Okay? But that means that the area of this new warped baseball diamond is the same as the area of the original one that's in green. Okay? And that's an important feature. That means that all of the relevant points that get moved, including the pitcher's mound, you see, will have to lie on an equilateral hyperbola using these as the x and y axis. In other words, this is xy equal a constant, where this is x and that's y, right? Okay? So this is the trace of where the pitcher's mound will go as we make more and more speed on Alice's and Carla's laser system, according to Bob. And there's no limit to this, mathematically speaking, you see. And I can go the other way too, you see. So that's a really important invariant to all of the transformations that we're doing here. The Lorentz transformation made out of the hyperbolic cosine and the hyperbolic sine. Now remember how the hyperbolic cosine and the hyperbolic sine came about. Hyperbolic cosine is the half sum of the left and the right lasers, one of which has been doubled to 4 and the other which has been halved to 1. So that gives you 5 halves. Okay? That's what you might call the arithmetic mean of those two. This is the hot laser, and this is the weak one, the low frequency, infrared and ultraviolet. Okay, is somewhere between 1 and 4. It's exactly a half of that difference. Okay, so the arithmetic mean of those two we draw simply by making a bisection of the 4. Okay, so with a ruler and compass we strike an arc. Okay, and that's where your pitcher's mound will be, at the top of that arc. And that's what you would do for any point here to make the hyperbola. You would simply stick your compass at whatever point you wanted to find the new hyperbola, and then with graph paper you go up and look, you see where the hyperbola was, but first you set your compass to the original pitcher's mound and strike an arc and stop right above your point, and that would be on the hyperbola. So this is Thales' construction here. A Thales construction based on the idea of the both the arithmetic mean and the difference mean. This is the other side of this thing here. The difference mean, the hyperbolic sign, is 3/2, in this case 4, minus 1 over 2. So it's half sum and half difference that make the coordinates for this new pitcher's mound. Okay, originally sitting here. Okay, now let's see if there's anything else that I need to say about that before we go on. This effect here, that the Doppler shift R times the red shift times the Doppler blue shift is equal to a constant, in this case 2 units of 300 terahertz. That's what we're using for our experiment here, thought experiment. That is a result of Doppler T symmetry. And we talked about that before. In other words, the fact that I have double that, I have to have this one. That is a T symmetry result, you see. Based on Evenson's axiom, you see, that all colors go the same speed. So I really want to make the point that we have very few axioms here. And they're mostly what Occam would be happy with. We have basically almost proved them. Almost. We've shown what you would have to pay for to not have them. And that is a lot. Okay, I guess that's enough. I am going to wait on that one because I think I've made it clear enough what is present here. But I would like to go on to this one and take on the geometry and make a distinction which hasn't been made before. And I wish I'd realized it a long time ago that this is a simpler way to get into the geometry. First of all, to point out that we have 4 parameters here that involve space-time. And those are the ones we're going to use because this is space-time that we're looking at right now. As opposed to per space-time, where the baseball diamond was originally constructed. Here we're looking at actual length, the wavelength of the phase part of this wave, the wave that really is going fast. Used to go infinitely fast, but now it's been slowed down so that it forms tracks in space and time that are tipped more than the speed of light. This thing will always be faster than light. These zeros that are being traced here will always be faster than light, no matter what I do with my Doppler shifting. But we're interested in the wavelength of those. In particular, we're interested in the wavelength, that is the horizontal length between where this one crosses and where the one preceding it crossed it. Or this distance right here, you see, they're always going to be the same, and that will be lambda phase. Meanwhile, the group velocity, the things that are colored green here for that g vector, okay, the slope of the g vector and the slope of the p vector at being looked at here, for those, we're looking at a much shorter distance. This is the length contraction that we were talking about before. It used to be 1, now has been brought down. The lambda group, the seek of the row, this guy right here, has been brought down to 80% of what it was. Okay? That clear enough? So that takes care of 2 lengths in space. Then here's 2 lengths in time, 2 intervals of time. Tau phase and tau group, the period of those 2 waves. And that just has to do with where they cross the vertical axis. There is the tau of the phase right there, and then the tau of the group, these guys, you see, have a different period, which is right there. So that is the quick way to see the geometry of these. Compare it to Bob's coordinates of Alice's G point and Bob's coordinates of Alice's P point right here. No jokes about the G spot, please. But anyway, these 2 things are actual points in space and time. Okay? And they are the sine and the cosine hyperbolic. All right? But over in per space-time, they were also components of a vector that was consisting of the half sum and the half difference, right? Things starting to fall together here a little bit. Okay? But these are the ones that we actually will be plotting when we're counting intervals between cutting of the axes by the zeros, be they phase zeros, which go faster than light, or group zeros, which go slower than light. Okay? So the next few slides will show that a little bit better. And that's where you see that there isn't much difference between these inverse hyperbolic functions that, like the Lorentz contraction, and the actual component hyperbolic sine that's indicated by the gray triangle here. There's the hyperbolic sine on this side. There's the hyperbolic sine of the tipped over triangle that goes with the phase, you see. There isn't that much difference between 0.75, you see, and this thing, the hyperbolic cosecant, okay. The hyperbolic cosecant is 1.33 here, and this is 1.25. This one is 0.75, and this is 0.80. We're talking about these, not that number right there, but, well, we've been looking at the frequency numbers. These guys range here, and that's per space and per time. This guy is the actual intervals seen on the cutting of the axes. And you can see when I draw it this way, it looks like I made a mistake and I ran too far over here. It's not a mistake. It is a little bigger than that should see. So that to me was one of the annoying things I should have noticed about 3/5. We'll go do 4/5 and get it straight shortly here. But that's what I'm saying here is that these parameters are so close they may be confused on the graphs. This is nearly equal to that. Then the inverse of them are nearly equal to. Which brings an interesting question. And that is, as you change your speed, how do these things vary? How can you get a feeling for that? Because there's a lot of slippering and sliding around going on here. And it helps to find a way to see that. But the first thing to do is just plot them. And I decided to plot them versus the hyperbolic tangent, which is the group velocity. In other words, plot it versus the relativity parameter that everyone old-fashioned uses. And let's just take a look here. We're looking at the possibility of the tau phase and the kappa phase being nearly equal, the sec being nearly equal to the sine, okay? the 3/4 and 4/5 is pretty close, but if you just go a little bit further, you see, we're right here at 0.6, okay? Right next to that line is a line at a certain value, 0.618, where they cross. So this hyperbolic C coming down like this, passing 4/5, okay, which is right there, and crashing into the hyperbolic sine, which is rising exponentially, essentially. They meet right at this point here, where we will solve the equation to find out where that is, okay? But they're already pretty close, and now they're right on top of each other. For this particular value, what is that particular value? A quick way to solve it is to notice that I can take the inverse hyperbolic cosine, multiply through, get that, and then put a 2 on that, and I've got hyperbolic sine of 2 rho equal 2, because I multiplied both sides by 2. So rho is 1/2 the arc hyperbolic of 2, which is that thing. Okay, and then you take the hyperbolic tangent of that to get the relativity parameter, u over c, the group velocity, and you get 0.618. You actually get square root of 5 minus 1 over 2. At the golden ratio velocity parameter, these guys run into each other. And so do their inverses. Okay, that's cool. All right? But then the actual value of that maximum is interesting. At this particular rapidity, the golden mean velocity, the two parameters become exactly equal to the square root of g minus. That's what that is down there, g minus. Okay? And 1 over the square root, because those were reciprocal. Okay? That's pretty cool. All right? And then there's an interesting coincidence right here at the square root of 2. And then this guy appears again, but this time it's the square root of the golden ratio, where we have another collision, okay, up here, where the sine runs into the hyperbolic cotangent. And also this one occurs, the cosecant runs into the tangent, hyperbolic tangent. So there's some interesting, numbers going on here. But physical significance, we might try to show a little bit of that. But let's just go ahead and take the quick view of where all of these numbers are. And this is definitely need this thing to be animated. That is, we need to have the lines coming out of the rhombus and crossing the axes, right? So you've got tau group there, you've got tau phase there, you've got lambda group here, and you've got lambda phase. Now you can just imagine how they're going to slide even without doing it, but you get a pretty thing. Meanwhile, hyperbolic tangent, and I didn't finish labeling this correctly. This is the V phase equal cot hyperbolic, and it's 5/4. That's correct. I just didn't get around to changing that. And of course, there are the coordinates of these P and G vectors. There's the P vector, the G vector, and now we're working with the hyperbolic tangent of 4/5. You're really clipping now. Okay, this is a very squeezed a Minkowski graph. Okay, I think
the order has changed.
Pardon?
Hasn't the order changed? Oh.
And they have definitely crossed each other and are getting ready to have another crossing, as a matter of fact. Okay? I forget which one it is. It is 0.8 and 0.75. They're about to cross. Okay? So that and this table is all available online. This will be online fairly soon. It's not not a difficult thing to change.
If you're viewing this video, it'll be in the information section, so it's all tied together.
Yeah, good. That's where we need to have it. Okay, let's go ahead now and take some animations up to see sort of real time, real space-time, what's going on. And that's this other program called Relativit, web simulation. And we're going to run it, and we're going to actually see a Minkowski graph. We'll start out with one that's not all squeezed, and then we'll look at Bob's view of this, which is this, okay? At 3/5, which is what we're talking about, and that will be, I think that's what I've got here lined up. So let's go ahead and do that on that screen. I'm going to bring this forward so that it can be cued in. And I'm going to set up on this screen right here the simulation that involves Bob looking at Alice, that is the weird one where you see Doppler shifts on both sides. And then we'll look at this one, which is what Alice and Carla see. So I'll click on this one to get this simulation going. Let's see if it's working. It seems to be pretty good. But this is what I used to use to teach relativity. I just imagined two lighthouses exactly a light second apart, and they key each other to start at every second. So, that's, basically a laser resonator, okay? And then what you're seeing over here is the actual plot with some hyperbolas and stuff drawn of what's happening. And of course, here we have an extra dimension in space. This is the x-axis. There's a y-axis in this plot. There isn't. The y-axis would be coming out of the screen in this plot. This is where we get to plot x versus time. Okay? And actually, I shouldn't have drawn time that way. Time is going down here. That got to be a reason for that is that now if you turn your head to the side, you've got a Newtonian graph instead of a Minkowski graph. You're always plotting x versus time in your calculus and UP physics, right? So that one is adjusted to make people feel at home after they've gotten done with UP physics, if in fact it's possible to feel at home at all. And then over here, I'm going to go ahead and start the animation as seen by Bob, who is moving at pretty good clip here. 0.6, in fact, is how fast Bob is moving. Now, this becomes a very useful sort of algebraic way of getting relativity if you pick half speed of light instead of 3/5, because then these two events, event 1 and event 2, occur simultaneously in one frame and not in the other, and that is a nice way to teach what's going on here. What I'm going to do though is reach down here and reset the animation speed to something fairly slow. So that we can talk about it. And I'm going to do the same with this one. But I am actually going to do something just to make this more better. I'm going to go here and pick lighthouse watches them pass at half the speed of light.
The dual view is one further down.
Oh, that's right. I've just got the. I need to get the
quasi-logical.
Yeah, let's do the dual view. That's what we've got on both screens here. And then I'm going to slow this down so that I can talk about it. And it's recycled, so when it gets done, there you see the two events that let's see how those came about, because then you can compare. And I might as well go ahead and do it with this one as well. You can see how all of this works. I'm going to go in here and get the dual view. Ship watches lighthouses pass at half the speed of light. So I'm going to pick that one right there, which is going now. Okay? But anyway, and I've been over here talking, it's just about ready to repeat. Then we can walk it through what's actually happening here and see what event 1 and event 2 are. And it's just about ready to run out and start over. Ship's going to start over here and move through, and all of this scenario is going to happen. Okay, bingo. Here comes the ship. Its nose goes right by the lighthouse at time equals 0 in this frame. Okay? That wave goes up, and they run into each other, which is interesting in itself. One little standing wave for. And then, at 1 second, there's another blink. Now, that event, the event we're looking for is when this first blink hits the ship's nose, which is right there. And at that moment, it's 2 seconds, because it's half the speed of light, and it's time for another blink. So you can see these two events are simultaneous in the lighthouse frame. And you can see that they are also that way when we graph them. Okay? So there goes the 2 blink waves. Okay? Here comes the ship. He's just moving along here. Okay? And then there's another blink that is going to collide with the ship's nose right about there. In fact, exactly there, at 2 seconds. You see? Bang. Both events occur at the same time because they're on the same time line, the same horizontal space-like line in both frames. But over here, the situation is quite a bit different. And as you can see, what's going to happen, first of all, okay, here we go. There goes the lighthouse passing the ship, making a blink, okay? And then here comes this thing, and it's a little bit late, but it gets a blink going, which immediately, very quickly, runs into the ship's nose. That's event 1. But it isn't until now that you get blink 2. Okay? Now on the graph, you can see pretty well how this happens. And the best way to do that is to complete the coordinate system here that represents the lighthouse's view of things. So I'll do that, but you can see there we're going to have another blink right there. It's not simultaneous with the hitting that occurred quite early right there, where that intersected the ship line. Lighthouse is over here. The ship is just standing still in this frame, and he's going to get hit by that blink number 1 right there, you see. So, just to make this really clear on this graph here, I've got to do some work on it. Namely, I want to show, and this is just a little adjustment that we can make, I want to show the ship's, the lighthouse's axis in grid. And while I'm at it, I'm going to go ahead and show the clocks of this as well. Okay, so we'll just reset start time equals 0 over here.
And pick it up. Let's start. This is the start button.
We'll just put the start button. There we go. So first of all, you can see the clocks are not synchronized on the lighthouse according to the ship, but that's because his coordinate system has been turned to first order that first order turn due to the hyperbolic sign is off diagonal in the matrix of transformation. This is what causes magnetism to first order. Magnetism is a first order effect in velocity, and it's because of this.
Oh.
Forget about contraction. You won't see that until you're really going fast. But first order effects you do see, and magnetism is one of them because it makes the charges be out of sync and have different distances between them. Okay? So that's an important piece of course, relativity. It's like with magnetism. We wouldn't be doing anything if we didn't have these light waves, which have that buried in them as well. So that's a, you know, something you can play with to really understand all the stuff we're talking about here. Okay? Well, let's go ahead. We've got lots more to do here. And what I'm going to do is I'm going to escape. I'm sorry, I'm going to go back here to the PDF. I can do either the PDF or the things on either one of these. And I'm going to do the same thing over here, just to not have distractions on either side. So let me take this one back to the, in this case it's a keynote presentation. And as you can see, they're about the same. Here's where I want to get you introduced to yet another way to look at relativity. But this one was very incomplete, and because of it being incomplete, because Epstein was not interested in row analysis, seemed not to be aware of it, and therefore not interested in relation between these two, which, you know, is really key. One of these is a transverse parameter. That's the, I'm sorry, longitudinal parameters. When we're working with a transverse parameter, which he's proposing, I label sigma to use more or less the same kind of symbol for the two of them, but one of them's turned sort of upside down. An observer going U will see a wave that is directly above with planes coming right down through this intersecting x-axis simultaneously. You will see that whole thing moved, and what's surprising, it moved in the direction that you have accelerated to get some high speed. Like in this case, the speed is pretty close to about half the speed of light. Now the speed of light is not going to change. The velocity is. Velocity vector is going to change. This is a c vector going straight down. You're going to get a c vector with a magnitude equal to c for this one. Okay? So, we already said that this u is c times hyperbolic tangent of rho. Well, the trigonometry of this says it's also c times the ordinary sine of sigma. Sigma is this angle right here. So that's the other way. You have a k vector here now that's tipped. Here it goes vertical. Okay? So that's the whole basis of this. As I say, you can get this book for about 14 bucks. Okay? Self-published. This guy couldn't sell this stuff. Insight Press is his father gave him money to have his own printing. So he literally self-published. I mean, he printed the books himself.
Is he a physicist?
Yeah, very funny kind of one. As I say, City College was a feeder school for Berkeley. People would, you know, not get into Berkeley because they didn't pass exams very well, and City College would get them all set. A lot of very good physicists came out, and then went across the street, so to speak, to Berkeley. Okay, so what I want you to see is a couple of the things. Time dilation, how does that happen? Okay, the way Epstein sees this, and I'll go ahead and finish the algebra that goes with it first before discussing the results. His trick is to turn a hyperbolic form, that hyperbola that we talked about, that involved, say, Bob's x and Bob's t prime, okay, being equal to Alice's time, and that would be a proper time that we're reading for her, okay. He says, turn that around. Put this thing on the other side with the proper time, and then you've got a circular form. Okay, you've got a regular Pythagorean sum, a squared plus b squared equal c squared, so to speak. Okay, and so the object of this is to think of a chart. Now, this is not a space. This is his whole book is made up of these kind of plots, where you have the x-axis, x prime axis, say in this case, and then you put the proper time for all of the observers. All of the observers each plot their proper time. And the idea is that according to this thing, everybody's going C. Everybody. Through this diagram. If you sit still, you just go C along this direction. C times proper time. And proper time is your time for this coordinate system. Okay? But if you're moving, you see, here's your CT prime, and here's your X. You've used up some of your proper time moving in this direction. And you're always on a circular horizon. If you're going the speed of light, you don't gain any age at all. Remember our phasors that are frozen? And you use all of your thing to just go to the distance. You gain no age. Wild, huh? Pretty wild. Yeah. But where it gets really funny is that every point, if you start every point, they do the same thing. There would be a sphere of possibility expanding around that one that would get that far while this one got this far. So if you have several different objects that are moving together, you have to rotate it. The rotation is by sigma. And so what you call Lorentz contraction, our Lorentz length contraction, you see, which was the sec of rho, becomes the cosine. Woo, that's cool. Okay, this is a relationship that he never seemed to gather. This is just a cosine of this. Wow, L cosine, okay? He figured, don't want to even look at the old way of doing relativity if you have this, right? That's a big mistake. He's missing out so much. I had him come here give a talk, and it was like talking to a statue. Nothing was going in. Time dilation. Our sec becomes, our hyperbolic cosine becomes a sec. That's this thing right here. Okay? That's Einstein time dilation. And you see it right here. See how this is longer? Okay? And then proper time asimultaneity, that off-diagonal component, the hyperbolic sine of rho, remember? Off-diagonal Lorentz transformation thing gives you a delta t. Okay? I measure it right here. You're out of sync when you're moving parallel. You're out of sync. Your clocks are slower or faster by this amount. And it's linear in rho. It's also linear in sigma. This cosine times that becomes the cosine of sigma times the tangent of sigma. Well, that's sine. That is the sine. Here's the cosine. There's the sine. Okay? It's really sad that this didn't get, in. This is Minkowski's plot should have been, available, right? They're not very available at all. Okay. Now let's look at the geometry of what we just did. This is this is where it gets really kind of fun. Rather than start this little thing up right away, let me go a couple of slides through this. But here's where I'm going to say I don't want an angle. If I'm going to work with space or space and time, I need to talk area. You know, degrees just don't cut it. And you'll see why, because when it comes time to do the rapidity, I need the area subtended by hyperbola. But let's look at an area subtended by an angle sigma on a unit circle. Okay, it's unit radius. Okay? Well, there's your good old sine. Okay? Then, if you draw a line along the tangent, where it hits the axis here is the tangent of sigma, which you can then rotate up and show, sure enough, it is the tangent. Here is the tangent, literally, of sigma right there. Sine over cosine. Okay? So far, so good. But what about this? What I mean by sigma is the total circular sector area of both of these sectors. That's sigma. This total pink area is sigma. Do you believe me? Bring it over here to pi and you've eaten up the whole pie, right? That's the area of the pie. Pi. Okay? Now, we're going to make use of all of this geometry, but what I want to show you is that this thing right here is on a hyperbola, the one we want. This one's x squared plus y squared equal 1. This one is x squared minus y squared equal 1. So our hyperbola that we got is tipped over. Okay? And moreover, the tangent to that one comes down here and hits right where that guy is sitting. And crosses at this point. The magic X, I call it. And this is the beginning of Occam's sword. Okay, that lets us see all of this stuff rather clearly. So, if we go ahead and look at this, I'm going to leave this one up here and advance on this one to that point and run it from that point. And then we'll come back here. But anyway, let me just click on this and see if it will bring us up. There we go. Okay, so there you can see this thing, you know, at work. Okay, and you can go all the way around. You make it on this side if you want. If you want to do some antiparticle work, you want to make it on this side. All your antiparticle stuff is down here. We won't talk too much about that, but that's what it is. That's negative time. Negative. Those are counterclockwise phasors down there. Okay. What this one lets you do is go ahead and put all of the stuff up there pretty nicely. There are all of the functions sitting there in their proper places.
Well, you can see the area there real well too.
And all of the areas showing. That's something I didn't mention is this is total circular thing, the pink area that has a circle. The total hyperbolic sectors area, and this takes a little calculus to show, but you ought to do it. That total subtended circular area, this is half of rho right here. The other half is down here on the antiparticle side. And that is our rho. That is what rho is. Rho isn't a dimensionless quantity, but for unit, it is that. If I scale it up, it scales linearly. Okay? So that's what we're working with, and that's really kind of neat. Here's a picture of them. And be aware, you see, that these things have this wonderful side. Notice the flip here. The stellar abline is what that's going to be. That's sigma, okay? The slope is the tangent of sigma, which is the hyperbolic sine of rho. This velocity line right here has a slope of the sine of sigma, which is the hyperbolic tangent of rho. Sine, hyperbolic tangent equal. Tangent, hyperbolic sine, also equal, but not to the original thing. There's another equality between those two, okay? And there's all four of the relations right there, all right? So that's you know, pretty cool. Now this tangent reciprocity right here is very important, where they cross there. That is connected with Legendre and Poincare relations. It's just high school geometry. And so is all of relativity and quantum mechanics at the fundamental level. So, I'll now go ahead and finish with these 16 incestuous parameter functions. They're all functions of each other, okay, in really marvelous ways. And we'll use it to just show how a waveguide can be mapped out. How spherical waves have the same Occam's sword, how accelerated radiation has it. And then we'll take a break and just go back and say, how would I teach this to a kid in high school? Well, American kids, they like sin. Okay, so we'll learn about sin. Okay? And then, by the way, we'll go ahead and learn about cosine, right? And they say, oh, I want to learn that. So, you know, we're trying everything we can to bring this country out of a toilet. But, you know, you got to do what you got to do, right? So, let's get started with Occam's sword, which is really quite amazing. Occam's sword is sitting right here. It's the one that's between the, shall we say, the velocity angle, okay? And when you turn this thing on its side, this is a hyperbolic cotangent. Remember, all of the stuff that we were doing was tipped over. Now we're back upright again. And then this one has a hyperbolic cosecant slope. So that's, you know, kind of weird, but that's just the complement of what we had over here when we were doing the original geometry. Okay? And that's the picture of it, and it's a very nice little construction here that builds that sword. The sword being, looks like one of those Turkish swords, okay, that contains a, you remember our staircase to make ratios? Mm-hmm. It's in there, and that ratio is the hyperbolic tangent. I'm sorry, hyperbolic cosine, or its inverse, which is the sec hyperbolic, okay? But anyway, all of these lines, these tangents and things, they all mean something very deep when we get to use them. Let's just take a quick look. I'm going to go ahead and try to run it on this one. It's a little bit iffy that I've run on a little Mac Air. But you can see a lot of the behavior of this when you play with this particular simulation right here, showing the blue shift and the red shift again. I'm getting up there, and my red shift is pretty weak there. You see, there goes that P point and the G points getting closer together. Come back to here, and they all line up. When you go contextual Monyo, which you can do with a right click, you can put a Minkowski graph in there with, say, one cell. Okay, let's look at that. When you click off of there, you can go and you can see that all this geometry is tied in very deeply with that Minkowski plot, you see. So these are some more stuff for you to play with that will help you do the understanding, which is the important part of all of this. Okay, now let's just very quickly breeze through some uses of this. Now remember, there's 12 of these parameters, but boy are they, shall we say, incestuous. Okay, and I believe this one right here is not quite in all of its glory, so I won't go ahead and animate it. We'll eventually get
a little
one.
later on we'll find a good one.
Pardon?
There might be another good one later on.
Oh, okay, I'll go ahead and see if it will bring us up here. The trouble is it has the darn table with all of its shall we say, things. I'm going to go ahead and go to per space-time.
Yeah, and show
Yes.
all, we can back out of it.
And then we can do all, right?
Yeah,
Um,
that'll layer.
and then I'll play with this. This is not too different from what we already had.
The hyperbolic plot type, when we went to all on that, if you go
That
yeah,
would be up
the
in
third item.
the third item, this guy right here.
Yeah, now doing all
Now doing
on the
all.
subtype.
Yeah, I think that will. Now, of course, the problem with this one is that it's tipped over. You see. Now the hyperbolic cosine goes to there, and the hyperbolic sine goes to there. But still, that's gives you a pretty good picture. If I'm not mistaken, it's this one right here, where if you go all on this one, actually this one right here, it shows all the slopes and everything.
Ah.
Okay, so this is really showing about half of the geometry. The other half's down here in the antiparticle region. But this is what you're working with in space and time. Pretty amazing.
All dancing in lockstep.
I mean, and of course be aware that, when we do our physics, we don't even move one pixel off of there, right? I'm already talking about 1,000 electron volts if I just go one pixel, right? You see, most of nature is carrying on in the astrophysics there. And then if I go down here, ultra-relativistic, if I go to the TeV region, I'm down in here. It gives you a real feeling of what, there's the whole field of physics right there. Somewhere. Right? Okay. So, let's get moving here, since we only have about 10 to 20 minutes left, depending on how you count. And I have Lorentz I should say Einstein time dilation at this point, right? You know how it is in a lecture. We've been, according to my clock, been doing this for 2 minutes. Okay, so I'm going at the speed 4/5, I guess. Anyway, this is a more compact circle-based geometry, which will also get programmed. It has certain things, but I just wanted to point out. Here's where it would work with a waveguide. Now, this is a waveguide where I've really got a steep stellar aberration angle. Now, stellar aberration angle is the angle that you come at. This is sigma right here, sigma equals 60. So I'm coming at a pretty steep angle, this thing. And as you lower your frequency, you keep having to reduce that until finally you reach cutoff. Cutoff is the frequency that's right there. This is the hyperbola that represents the dispersion function for the waveguide. Okay, this is a TE mode that's being shown here. The K vectors upward and downward are indicated by the blue arrows, okay? And the wavefront's crest and trough are indicated by solid lines for crests and dashed lines for troughs, and you can actually see the trough of the wave and the crest of the wave sort of sketched in there. This is all available on Guided, which I forgot to include.
2 pages.
The
First links, 2 pages on.
definitely need a link on here to that.
2 pages further on.
Oh, good. Okay, we'll get a chance to take a quick look at that.
Yeah.
This is a waveguide that's got a really big occam sword. The angle is pretty shallow. This is close to 90 degrees. Obviously, if you can get your frequency higher and higher until it's finally optical frequency, you can just go straight through a waveguide and forget about the walls. But in the region that causes a resonance for the waveguide, you're going to have an angle that's very strictly determined by the frequency. And this is the geometry that lets you get that. It's just sitting right there really beautifully. And here's a almost dying laser. We're really close to cutoff, which is the bottom of the hyperbola here. We have tiny little occam sword there. and a very steep angle, sigma equals 30 relative to the vertical, which is what we measure sigma at. And here is just to compare the two of them right here. Example of near cutoff mode with a low group velocity and a high phase velocity. All of those things are available on OpenSort for a waveguide, and it's really a powerful thing. And then let us go ahead and just see if we can actually see anything. There we go. Now you get an idea what group velocity is. Group velocity is a lot slower than the phase velocity. Phase velocity is outrunning it right here, you see. And the group velocity is simply what a pulse would do if I made two frequencies that had a little pulse there. We've got this thing like a drunk going down the cavity. It's going C, but it's got such an angle to it that it ends up having a very slow group velocity compared to the phase velocity here. And all of that is indicated by just that little diagram right there, which was the one that begins our trigonometry. So this is something to know, okay? Now, as I said, we're running out of time, so I want to get to the main thrust of all of this fairly quickly here. Let's come back and go ahead and look at the spherical waves. Now, we already did this simulation. Okay, there's the lighthouses, right? And if you're moving the lighthouses, crowd the waves in front, right? And I'd like to look at that geometry a little bit more too. But there's your Occam sword right there that determines what everything is. There's your sigma right there, and then there's the velocity thing, the speed that's connected with the angle that's associated with this particular speed here. This is a velocity angle u over c, and it's 3/5 for like all of the ones we've done so far. Here is, and this one I do want to show. This is really beautiful because this is where the Occam sword shows up in space and space. So it shows up everywhere. It shows in space and space, space and time, per space and per space, and per space and per time. All the possibilities, same damn geometry.
What about per time, per time?
And there's only one kind of time, so we can't, claim time and time. Yeah. Yeah. But anyway, here, if you see, it's like I'm rotating a cone. There's the cone straight on, okay? And then I'm getting really high speeds here. And here is the ellipse that determines the transverse Doppler shift, which there will be as you make a bigger Occam sword. As you make the Occam sword really big, you're going to have a heck of a shift. And that we'll show next, in the next little vignette. Let me go back to the talk and go ahead here to this. This is really cool. This is where you get to see what looks like on a Stanford accelerator right now, where they're doing experiments with spectroscopy. As you get your speed up, you get a pencil of light. This is the synchrotron horn forming right there. And that ellipse is right where its focus is. All this geometry ties in. The Occam sword now comes out of the focus of the ellipse, as well as out of the origin. There's another one that goes the other way. And then there are the colors that you can see. Those are the actual visible colors, starting with 600 terahertz right there, and shifting the thing, the UV being stuff you're going into, and red what you're going away from, and the rest of it, this would be invisible to the human eye, the black. But it's there nonetheless. Okay, that's just to give you a little bit of a feel for the power of the geometry for this. And there's a nice drawing of what we just did. Now, let's sin a little bit. This is the way I'm going to start the honors course. Learning about sin. And this, if you want to sin, you got to push the sin button, right? Okay? So you pick an angle to sin at, and you're off to the races. And in this particular case, you get 0.5 as a result of pushing the sin button. And that is an indication of what is called a slope incline. It's so highways are measured by, this is a 50% grade, okay? You go up this far and half that is gained in altitude. That would be called 50% grade. And I think sin stands for slope of incline, but who knows, okay? And then there's the complementary slope, okay? I mean, you turn your head on the side, and then you're interested in that one, okay? And so you can sin, and then you can have a cohort to sin with. That's cosine, and this one comes up with 0.87% when you turn your head to the side at 90 degrees, a complementary slope of incline. And then here comes the tangent. Remember how we dropped the tangent off of there, and then rotated it up, right? That comes in here at 0.577, square 3 over 2. And next comes the complementary tangent, okay? And then the complementary secant. Secant, remember, is the distance that is being soared going through or something like that. I can't give you all of the etymologies of these things, but there are your functions, and of course they're not direct keys. You have to do the inverse, get those. So here's the situation that we're looking at right here. Cos is the sec of sigma, sec of the rho is cosine of that. They all have their partners, you see. They give the same result, same result, same result, same result, da, 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 okay? And so interchangeable, completely interchangeable to use rapidity or the stellar aberration angle, regardless of how fast you go. And what's really cool is they all have meanings in mechanics. So this is where you've taken something that's really hard, really complicated, very mysterious in many ways, and reduced it to child's play. We got to do more of that because we have so many things that are totally mysterious in science. Okay, we got to break it down. Okay, so here's where I'm going to go ahead and derive the relativistic mechanics. But it's the mechanics of quantum mechanics that we'll be making. And let me show you the logic of that. We're going to take our table and we're going to use it. And I've pointed out to you that the phase frequency is something that is not classical. It's the heartbeat of some sort of piece of matter. Now the piece of matter that we have is what's inside a cavity. So I've got this cavity, I've loaded it up with a heck of a lot of light, and you're always told that relativity tells us that if I load that cavity with light, it's got energy in it, therefore it has more mass. The empty space of that cavity has mass. And that mass is due to the heartbeat. So we're going to pick new phase to look at. And while we're at it, we'll look at kappa phase as well. The phase, that's the thing that classical Newton didn't know about. But we do. Okay? Because we've been playing with light. Carefully playing with light. So we're going to look at Newton's speeds with the sine hyperbolic and the cosh hyperbolic being our interesting functions. Okay? Both involving the phase. Okay? And low values of rho, I've got a quadratic function with low values of rho. I've got just linear for hyperbolic sine. Next one will be cubic. So to second order, this is what we've got. We're looking at here. And then while we're at it, hyperbolic tangent, also linear in rho. Okay, exactly linear in rho. Okay? So, whatever this base, that's the base of the hyperbola for the hyperbolic cosine, whatever that b is, this is what we've got. Okay? Now, to use our old notation, the b is nu Alice. the frequency that Alice has in her laser, 600 terahertz, okay? And it's also C kappa Alice, okay? That's just a characteristic of the light that we're dealing with if we're not moving. But if we're moving at rho, we're going to get all this stuff. Okay? So what is new phase? New phase is B times 1/2, that's 1/2 from there, and then I use the rho here, which is U over C, 1/2 U squared over C squared. Okay? This is for U much less than C, remember, low speeds. Okay? And kappa phase is just U, but with B over C squared. So we got a B over C squared U squared, and we got a B over C squared U for these two quantities at low speeds. And as I say, we're only moving a few pixels off of the top of the hyperbola there. This is good enough. It's good enough for Newton, not good enough for us. Okay? Now, as I say, they resemble Newton's formulas. If we just adjust something, we multiply them by something. Okay? One of the things we have to do is scale it. Okay? We're going to rescale this guy. Okay? I'm attaching a scale factor to match the units so that I really am getting what Newton called energy, 1/2 mu squared, constant plus, and then what Galileo would have called momentum. So here's how we make the connection between these quantities. The energy is connecting up with new phase. The momentum is connecting up with kappa phase. See where we're going? Okay? But we do have to put that scale factor in there. We attach a scale factor H to match the units. Something joule seconds will do it. Okay, so I end up with this. So I have a kappa phase equal to that. I have a new phase equal to that with that H scale factor. All right? This is where the famous MC squared shows up. The scale factor of the base of the hyperbola is MC squared. Okay? Then we'll go ahead and put that in here. This is what's giving me momentum and the MC squared plus. You see, that's the HB. Right? Now you say, is this a lucky coincidence? Is this a cheap trick? There are lots of things you can do in physics that do some pretty amazing things, and they just turn out to be tricks that don't go anywhere. So we have to check this, because we've only done it for approximate values. Try exact new phase. Okay? Exact new phase is that. Okay? So what this is telling me is that that's my exact new phase. Okay? But in old-fashioned notation, that's that. We've just taken care of two major results in physics. Planck's axiom, almost Planck's axiom. There's something has to be done to that. Put an N next to it, because it's a wave and it has to fit in a box. That's your quantum number, first quantization. But this is the energy. That's exact, old-fashioned notation. This is the new-fashioned notation. So much better, right? Because you just punch one button to get this. How many buttons do you have to punch to get that? Okay? So, you know, we're a button-pushing society. I'm going to reduce the number of buttons pushed. Okay, now we need to replace H with H nu, Hn, to match EM energy density. And this is electric field dot electric field epsilon 0 equals this. Okay? And this motivates the idea of normalization. E squared is psi squared, provided you set the psi to this. This is called the quantum field constant. Okay?
Electric
Once
field.
you set that, you're all set to do quantum field theory.
It's electric field per quanta, right?
Right. Exactly. Exactly. But it does bring up a big worry. And this is the worry that, you can see this guy looks really worried. Because after he presented this H nu N, he said, what am I doing? I know that harmonic oscillator, which is what the field is quadratic in frequency, not linear. What's the matter with you, dumb cough? He was totally depressed. If he's like Boltzmann, he would have killed himself. Boltzmann was a manic depressive. He was a little stronger than that. So he didn't. And Einstein comes and saves his ass. But here's what the resolution really is, and it wasn't realized for a long time. The dirty secret is that E field amplitude, the N, and the new phase, these are all frequencies. The N is the frequency of counts. It's also going to Doppler shift. So if you're a product of N and frequency, and that is quadratic in the frequency, then that's how you're going to transform. You're going to transform not with just e to the rho when you Doppler shift, you're going to transform e to the 2 rho. This is quadratic in the frequency, even though it doesn't look like it because there's another frequency right here. So I don't have a picture of him not looking worried, so I can't fix that for, but that's the basic idea. Now here's the other side of the story. It comes 24 years later. Okay? Let's try exact kappa phase. We did the new phase and got something. Kappa phase has got to be de Broglie. Bingo. This is 21, okay? This is 1905. Actually 1900 for just that. Okay? So you see, if we're going to teach this stuff, we don't need to go through always go through what the path was of these guys. Okay, now, as I say, these are important points too to make. And here is another important point, is that we don't get very far in most of our work, so we get to use Schrodinger. It's a parabola or a circle, and most of the time we write it as a parabola. Okay? And underneath it is the real bugger, and that's the other half of this, and that's how you make matter that you can don't have to keep the laser on for. So here is the idea. A table of things, okay, that have various interpretations. This is the Einstein time dilation, this is the Lorentz contraction. This is the past few asymmetry, its first order in its variables. Okay. Now what I want to show you, I complete this, is how it is, how much do we get by knowing that this one is a momentum, this one is minus a Lagrangian, this one is the Hamiltonian, and this one is our de Broglie lambda. And that means that we can turn momentum to de Broglie lambda. And everything in these tables, this is the reciprocal of that, this is the reciprocal of that, this is the reciprocal of that. The same table, just renamed. One little point here. The elephant in the room. What is the matter with mass? Mr. Elephant. This is a Republican just collapsed after his debate. Okay, he says, "I matter." Sounds like Trump, right? Okay, so we want to know how much mass what are we talking about here? What is this rest mass? I already says it's something to do with the heartbeat, the extremely fast heartbeat associated with mc squared. Okay, so that's what we call rest mass. Okay. That's a really new concept that would have blown Newton's mind, but we've gotten used to it, okay? But let's look at momentum mass. That's defined by the ratio of P, that's mv, over v, mu over u, okay? That becomes m, okay? But it's m associated with momentum, okay? And we're going to use relativistic momentum, and we're going to use group velocity, okay? There's your group velocity, derivative of nu with respect to kappa, or omega with respect to k. Okay. Here's the Cp, the momentum, okay, mc squared hyperbolic sine, we're going to use that, okay, and it's h bar c kappa phase by our recent calculations, okay. So we've got this, sine hyperbolic over tangent, oh my gosh, Only thing survives there is a hyperbolic cosine. Okay? That's momentum mass. You've seen that before, right? Everybody says, oh, you get heavier when you go fast. Okay? Limiting cases. It's approaches exponential. As you go faster and faster, it blows up. It's horrendously high. Okay? In the middle of a hydrogen bomb, you have an incredible mass. And that's what makes it so dangerous, because it then goes and digs holes and things. Okay, so this is the momentum mass. Now, what about Newton's mass? Defined by the ratio F equal ma, but basically F over A, frequency, force over acceleration, okay, which is the rate of change of momentum, okay, dp du, okay, dp is this, du is that, put them together, you get cosh cubed. That's effective mass. Now, that one goes up as 3 rho. This is really something. That's the kind of mass that it's going to be different from all of these become the original rest mass at low speeds, but at high speeds they go bananas. Okay, more common derivation uses group velocity. Okay, and what you get is this. This is a very general wave formula for effective mass of any dispersion function that you have. It's inverse curvature with h bar in the numerator. This is a quantum result. Okay. If I'm using omegas, it'd be h without if I was using frequency. Okay, so this one is cosh cubed, effective mass. These two accompany each other. Group velocity is the derivative, and omega with respect to k is dispersion function velocity, and this is the curvature, but it's in the denominator. Very weird. So, how much does a gamma photon weigh? Our 600 terahertz photon. How much does it weigh? Rest mass. 0. Okay, that's the, it's a hyperbola, it's degenerate, so 0. Okay, momentum mass. Oh, I get something for that. P over C, h bar k over C. Put my frequency in here with h bar and the c squared. Boy, I get a small number from that, as you're going to see right there. It is 10 to the minus 36 kilograms per cubic meter of this stuff at 600 terahertz. Okay?
Dr. Harter, so this rest mass comes from heartbeat, right? The phase.
Yes.
Right?
Just the heartbeat that's left after you caught up with this box of light.
So,
right. So it's just, that's all it's doing. It's
so
just going up and down.
the photons will have this phase.
Well, how many quanta does the oscillator have? So there's a hyperbola for the ground state, right? It has a half, right? Omega. Then there's the next state, and the next state, and the next state, and the next state. I'll show pictures of that in a minute here. But that's what you mean by photons. So what we're talking about here is basically mass per photon. I've had one photon in there, and I really have 3 halves because I've got the 0-point motion. And I've got more than that because I've got 2 dimensions, you see. So, you're cool about the coefficients. But it's got a very small number. Not something you're going to ever, I think, in our lifetimes, directly measure. Okay, now, this stuff, I can go through this fairly quickly because we've been through this so much already. But remember, the phase that we're working with immediately gives you Lagrangian as a derivative of that total phase with respect to time. It's a total derivative. P is this, E is that. Those are the relations that we just got. We're using h bar now because we like to use omega sometimes. And the Legendre transformation is what comes out of that. Okay? This is all just simple algebra. And then I put the group velocity in, multiply the two together. Okay? Do some algebra, and come up with a Lagrangian that says seq. Okay? Minus the seq with the base mc squared. Okay? And then the Hamiltonian, we've already talked about that, but there it is again, hyperbolic cosine, same coefficient. Okay? There's another way to write it. There would be Epstein's way of writing it, if you were to go ahead with this. A cosine and a secant is kind of interesting. But what it really shows, as I want to get here, is that the Lagrangian is a circle. Okay? There's the circle for the Lagrangian. This is where it happened to wind up for that particular value. And there are the two equations. Here's the Hamiltonian. The derivative of the Hamiltonian with respect to momentum, remember, it has to be a function of momentum, Hamiltonian, okay? Whereas the Lagrangian, which is down here, this thing right here, there's the Hamiltonian right there. It's the cosh or a secant, depending on whether you want to use angles or not. You definitely, for the Lagrangian, want to use sigma, because there it is sine and cosine of sigma. Remember, sigma is the angle of the stellar aberration angle. That's this line right here. So you use polar coordinates if you're going to play Lagrangian. And you can play that game all the way to high energies, where the sigma is almost 90 degrees. So there sits the thing. And of course, there's the positive Lagrangian right there. This is the negative Lagrangian right there. This has the same curvature as the hyperbola. So at low speeds, you can't tell them apart. And if you throw away the mc squared. You throw away minus mc squared in case of the Lagrangian. And then all of the Poincare relations and things like that, including Jacobi equations, they all come and they have nice significance for this stuff. Transitions. This is where we're getting a little bit over time, but I'm going to go ahead and just show you that the same geometry is if you jump using light. You always jump at 45 degrees. So you make a transition from, say, this hyperbola that went through there to one that's down here, and that's where you hit. So you don't quite get to the rest energy. You have some extra kinetic energy because you gave it some momentum. And then the light flies away as a result of that. The Feynman diagram for this would look like that. And this is a geometry for it. So here's the closed triangle. There's the open triangle, which is a Feynman diagram. Scaled down from this one, just so it'll fit in the page. Okay? So what you can do with this is notice that all we're doing here is using the symmetry of waves, and that is you do not change the wiggle count in space or time. That's really what it boils down to. So that was a classical postulate that you could not prove classically, but you can prove it, and you can show that within uncertainties it's right. But here's the really cool thing, is that you go ahead and present you have a Doppler shift involved in that transition. Okay? So we want to compute the rapidity of the recoil velocity from a particular transition. It's really easy to do. There's the answer, basically. Okay? But I turn it around, so I get rho is equal to logarithm of the mass ratio.
It's a rocket.
And rho is very nearly equal to u over c, so I get this equation right here. Now you've seen that before.
Mm-hmm.
V burnout is c exhaust times the logarithm of mass ratio.
Perfect.
That cool? So you think of a light coming out of a thing, it doesn't go, it goes and resonates, right? There's this tremendous heartbeat time for each of the emission processes, right? When you're, particularly if you've got it in a situation where it isn't being disturbed. Okay? So you get this exact recall is this, approximate recall is that. So this saves pages of work when you do calculations for recoil and all that kind of stuff, Compton scattering. And I'm looking forward to the days when I do that. So here's a situation where we have a bunch of hyperbolas in a cavity, various modes that make it up. This is very much like a molecule, except it's just light in a box. And there's the first quantized quantum number, and there's the second quantized number that just come. And that's kind of a picture of the modes there. It's based on the functions of a harmonic oscillator in a sketchy sort of way. That's a whole course for that. If you want to accelerate, you laser tune. That's what I'm imagining here, that I would just have two lasers and I would keep tuning them to make this thing have different velocities, this frame have different velocities. It turns out to be a really simple thing to do. The previous examples involved a constant velocity, and that just gives you a uniform Minkowski graph in a straight line between them. But if you raise them in a constant sort of way, a uniform sort of way, actually an exponential sort of way, you get this situation where I'm going to put Alice over here chirping up, and I'm going to put Carla over here chirping down at exactly the same proportion with each other. And this is just a schedule for their chirps where they when they should do their chirps, so that the light comes up the light cone and meets right here. It turns out it'll meet right on a hyperbola, constant G hyperbola. And you can prove that other ways. If you just go ahead and integrate the equation that was on the previous slide, which I won't go back to, but this is really neat. The area here, remember we talked about area, okay? We're using half of it, all right? That's the key thing for getting, you know, where you are, no matter where you start. These accelerate, a constant acceleration, going Al, Bob, and Carl taking off for the wild blue yonder. And the idea of this is shown in this little movie right here. There they go. And what's interesting is they think they have the same distance between them all the time, but their times are not the same. When you live downstairs, you age a lot slower than if you live at a higher level in the, shall we say, New York apartment that's being accelerated at, in this case, 1G. Just imagining 1G. 1G leaves you with a light year here. That's a big distance.
So the fine lines
and
inside...
this is the event horizon right here for that curved coordinate system. That's the singularity of this thing.
Your fine lines then would be the wiggle count in both space and time, depending...
Yes. Yes. I mean, it's just CT versus X in Alice's and Carla's coordinate system. And they're shining in light that on one side, they're raising the frequency. That's Alice. And she's lowering it, getting more and more into the infrared. Builds an optical coordinate system that has the kind of coordinates they use to go into a black hole. Okay, I think that is about it. I'll go one more step here just to show you where we imagine that when they reach zero velocity in Alice and Carla's coordinate system, they drop a wrench. In other words, just put a wrench outside of the spacecraft, which then never moves in Alice's coordinate system. So it's just a straight line up. But of course, this guy right here will hit Carl. Dan will hit Carl with that wrench right there, and then the wrench goes through and keeps going on the same speed relative to them or anybody else. Here it is. Bob gets hit, and then finally Al gets hit. So those are all mechanics problems that you could do in this weird, most simple curved space-time coordinate system built with light. And we're still wrestling with some things on this. Once you do this, you see all kinds of things that you have to really wonder about. So I have many doubts about things that happen even here in what's commonly known as Einstein's elevator. This is a quantified coordinated Einstein elevator. Well, I hope you've had fun with this stuff and continue to do so with what we've left on the web. And always entertain questions.
Sure.
Maybe I'll entertain you with answers, because there are a lot of things that I don't understand about it too. Perhaps you can help me. Thank you.